This time we're going to talk about acid strength. We said before that some acids are strong, some acids are weak, some compounds don't donate H plus to water. Why is that? What's the basis for that? We just sort of accepted that. We use Ka as a way of gauging whether an acid is strong or not, right? So before we go into the actual molecular explanation, let's first have some kind of basis for comparing the strengths of acids. Okay, let's calculate what we would call the Ka of hydronium ion if we were going to so that we can make a valid comparison. Okay, remember when we said what was the when we talk about the ionization of the acid. So if you have an acid HX, for example, the equilibrium constant, okay, which we call Ka, is what? It's for this reaction. HX plus water gives you H3O plus X minus, right? So the extent to which this reaction occurs, the equilibrium constant for that is called Ka. So we use that as a basis for determining acid strength. The larger the Ka, the farther this goes forward, right? And we said that for strong acids, that number is really large. In fact, for HCl, okay, that's at least 10 to the 6th. So just for comparison, so we can make a basis for comparison. Let's calculate what Ka for H3O plus is going to be. If I have H3O plus, I react that with water. Okay, it will have to it will transfer a proton to water. What will I get? I get H3O plus again, and I get water again, right? Now you might say KEQ for this should be 1. That's correct, but if you want to compare it with the other acid, let's pretend that this H3O plus is actually H plus H2O. So your H2O is your X, okay? So we're going to treat this H2O as though it was X. So we're going to use concentration of H2O instead of the activity of 1, okay? Just so we can compare the Ka. And if we did that, okay, so your Ka then you would say is H3O plus times H2O divided by H3O plus. So H3O plus concentration is just going to cancel out. So the Ka of the hydronium ion is just the concentration of water for comparison purposes. And that's 55. Where did I get that number? Concentration of water. Moles of water over volume of the solution, which is just going to be the volume of water, right? Okay, if I have a mole of water, how much volume does it occupy? A mole of water is how many grams? 18 grams. Okay, and how many mils does an 18-gram sample of water occupy? What's the density of water? 1 gram per mil, so 1 mil per gram, right? Is the volume per gram. So what is 1 over 18? And let's change this to liters because we want to do moles per liter. So times 1 liter over 1,000 mils. So that ends up being 1,000 over 18 moles per liter. What's 1,000 divided by 18? 55, right? So we say that the concentration of water in water is 55 moles per liter. Okay, so just for comparison purposes, we can say then with the other acids, we say put on the same scale, hydronium ion is going to have a Ka of 55. So anything that has a Ka of 55 is what you would call a strong acid. Okay, now what would be the Ka of water itself? Well, you'd say that for comparison purposes, you're going to say water plus water. You proton transfer, you have H. So let's think of water here as HOH, okay? So HOH, this is our X, okay? So that gives you H3O plus, so that proton drops onto that water molecule, plus hydroxide. You might say, that's Kw. Yeah, it's Kw, the KEQ for that is Kw, but like I said, to compare it with the other acids, we're going to treat this as though this is X minus, okay? So that's your X minus. So Ka then would be hydronium times hydroxide, which is X minus, over this water right here. Okay? So you do know that in water, hydronium times hydroxide is 10 to the negative 14, right? That's hydronium times hydroxide. And the concentration of water, we just figured that out, is 55. So that gives you 1.8 times 10 to the negative 16. Okay? Note that that is a very small number, right? We say water is a very weak acid. Okay? It has a low tendency to transfer proton. Hydronium is much stronger acid than water, right? In fact, hydronium, we say, is the strongest acid that can exist in water. Any other acid that's stronger than hydronium, like HCl, is just going to give up its proton right away. Because there's so many water molecules there that can pick up that proton to give you hydronium ion. Okay, so anything, so if you have a species, for that to be able to yield H plus in water or hydronium ions in water, it must be a better proton donor than water. So what we call weak acids are those acids that have a Ka larger than 1.8 times 10 to the negative 16. They're better than water. The strong acids are better than hydronium. Okay, so you can use, on the Ka scale, you can use these numbers as a gauge whether it's something's a weak acid or a strong acid. Higher than 55, strong acid. Higher than 1.8 times 10 to the negative 16, that would be a weak acid. Below 1.8 times 10 to the negative 16, like ammonia, for example, okay? If ammonia were to donate a proton to water, that will give you the amide ion plus hydronium. The Ka for this is extremely small. Ka is less than that for water. So ammonia doesn't give you an acidic solution. In fact, what ammonia does, it rather takes proton away from water instead. Okay? So what makes a proton donor then?